through a sorting problem posted on Reddit by Cosmologicon. The problem asks us to create a pancake sort. The first piece of that is to create a flip front function, which reverses the first n elements of an array. So if we take a look at one of these examples here, 0, 1, 2, 3, 4, flipping the first three elements, reverses the 0, 1, 2 to 2, 1, 0, and leaves the rest of the array alone. So let's jump in and create this function. Let's start with the signature of the function. So we'll define a function called flipFront, which takes an array as a mutable reference to a vector of u32. And it'll also take n, the number of elements to flip. We don't need to return anything because we're taking a mutable reference to the array, so we can modify it in place. Our check case will be if n is 0 or n is 1. We don't need to do anything with this array because rotating 0 or 1 elements won't change the array, so we'll just return. Otherwise, we need the midpoint that we're going to rotate around. So we'll convert n to a floating point, divide that by 2, and then we need to compute the ceiling of that, and convert it to a u size so that we can compare in a minute. Then we'll loop through from the first element in the array up to the midpoint, and we'll keep track of the element we're going to do a swap with. And then we'll create a temporary variable for the swap. We can then move the element from the back to the front. There we go. Tidy that up. And then lastly we can tidy up the swap by putting the element from the front to the back. We need to check that works. So we'll define an array as a vector of 1, 2, 3, 4, and 5. We'll flip front on that by passing a mutable reference to the array and flipping the first three elements. Then we can print out the result. Let's have a look. So we'll cargo run the project. And it does what we hoped it would. It prints out 3, 2, 1, the reversed 1, 2, 3, and leaves the rest of the array alone. Now we can think about the sorting problem. So if we take an array that has 3, 1, 2, and 1 as its elements, how can we sort this using flip front only? So there's really only two things we can do. We can either flip part of the array to move a number to the front, or we can flip the whole array to move the number at the front to the back. So looking at this first example, we can call flip front once to move the 3 to the back. Then we can call flip front on the first two elements to move the 2 to the front. And then we can call it a third time, flipping the first three elements to move the 2 to the third position in the array. And the array is now sorted. The next piece of code we need is a function that can find the maximum value in an array and tell us what the index of it is. So we'll define a function, index of max, which takes an array as a reference to a vec u32. Notice it's not mutable this time. We don't need to change the array in this function. And we'll define an index limit. This prevents us searching too far through the array, and will return the position that we found the max element at. So let's keep track of the max element, and that will need to be mutable. And we'll keep track of the index that we found the max element at. Then we'll loop through all of the values in our array up to our index limit. Turn our index limit at this point, our max limit even, so that the compiler is happy. And then the logic in here will be if array at current position is greater than our max value, then the max is now the current value, and the index we found it at is the index we're currently working at. That's all the groundwork, so now we can start building the sorting function. Let's create a pancake sort function, which takes an array has a mutable reference to a vector of u32. We're going to track the working index, so we'll start with the last element of the array and work backwards towards the front, trying to leave each element sorted as we go. So we'll start with the last index, and then we'll work down until almost 0, noting that the last element doesn't need sorting because it must be the smallest if we find all the biggest elements and put them to the right. Then we can find out which index we want to sort next by calling our index of max function with the array and the working index to prevent it looking too far into the array. We don't want to start sorting things we've already sorted. So our max index is that. Then we can use 2 calls to flip front to move that element to the back of the array. So we'll flip the number of elements to include the element that we found that we want to sort to the front of the array. Then we'll call flip front again on the array to move the element that we just moved to the front back to the back of the working set. And then we'll decrement the working index so the loop can run again. We do want to add one more thing to this function, which is to keep track of the number of times we have to call flip front. So we'll define a variable to keep track of that. After we've called the function, we'll add 2 to calls count, and then we'll return that value at the end of the function. And we'll make that a usize. Let's make sure that works. So we'll define an array, which is the one from our example, 3, 1, 2, 1, and then we'll call Pancake sort on that. And that needs to be mutable reference. And we'll keep track of the number of times we had to call flip front. And we'll print out both the array which should now be sorted, and the number of calls we had to make. Let's jump over to the terminal and run that. So if we run the program, we see that our array has been sorted and that we made 6 calls to flip front. So certainly not an optimal implementation. We know it can be done with 3, but it's working. We should test this on a bigger input, so I've written a short function here that loads a file called input.txt, and that contains 10,000 numbers, all on separate lines. So we'll create a buffered reader, allocate an array of 10,000 elements, then we'll run through every line in that file, create a number from each of those input lines, and that'll give us some data to work with. Let's go ahead and use that function. So we'll call load test input, and that'll give us back our test array. Then we can call our sort on it. And that needs to be a mutable reference. And we can capture the number of calls we made. And let's print that out. We'll kick the program off with cargo run, and this time it's going to take a little bit of time to run that data through. But it does come back, and it's taken nearly 20,000 calls to flip front to sort that data. So can we make this behave any better? We're going to make a change to the index of max function, which is less of a well-reasoned change and more of a thing that behaves better on this data. Rather than selecting the first value that's our maximum, we're going to select the last value that's our maximum. So if we keep finding more values that are equal to the max, we'll keep updating our index. Then we'll define a Pancake sort v2, and we'll make some tweaks to how that behaves. So first we want to call our new max function. Then we want to think about how we can reduce the number of calls to this. So the first thing we could do is if the max index, so the number we want to move into position, is already in the right place, we could just decrement the working index, so skip that position, and continue out of the loop. We could also think about what could happen here. So if the number we want to move to the back of our working set is already at the front of the array, we don't need to do the first flip, that's pointless. So if max index is not equal to 0, then we need to make that flip. Otherwise, we've saved a call. Then we should add some code to verify that. So let's load a new copy of our test input. Because bearing in mind we have already sorted this one in place, so we can't reuse that array, it's already sorted. Then we'll call our Pancake sort v2 on the new test array and grab the calls count. Let's give that the same name as the other ones. There we go, and we need to remember to make this a mutable reference so that we can modify it in place. We should quickly test that our optimizations haven't broken the program. So test array should be equal to test v2 array, otherwise we'll print an error message. Not equal, not sorting. And then we'll print out the number of calls we made to the new test variable. There we go. Let's see how that does. So we'll kick that off. And we think we probably haven't made that much improvement, so it's going to take a little while to run. Okay, so we've only actually saved 47 calls, but we've got down to this number, 19,951, which is around what people were getting on solutions they were posting online. Could we do any better? Coming back to our original array, we can see that our code will now spot when the 3 is at the front and just do a single flip to move it to the back because it's in position 0, and the 2 will require 2 flips, there's no way around that. And then handling the 1 here, which is our last maximum element in the array of our working set array, that will get ignored because it's already in the right position, and then we don't process the last element in the array because that must always be the smallest. So we've made the program as efficient as it can be for this small example, but it could be made better for the large array. There are some more optimizations, and if you want to go and have a look at the solutions people have posted on online, you can. The solutions that do better than this one consider more than one element at a time, so blocks of elements that are a group that can be flipped together, particularly elements that are the same value. But that requires so much inspection of the array that it's really not a useful sorting algorithm at that point. To understand why this code isn't particularly efficient, we'll consider the complexity analysis for it. So space-wise, it's pretty good. We take our arrays by reference and we mutate them in place. So the most we're ever storing is a few variables to track what's happening, and in the case of the flip front function, we store a temporary variable as we flip each element around, but we don't really use much more memory than the size of the array, and it's constant, so if you increase the size of the input, you need the same amount of extra memory to run the program. The time analysis is more interesting. So if we look at what's happening here, we have to run through the entire array. So if we annotate this as we go, this is n-1 because we're not processing the last element of the array. Index of max, that is running through up to the whole array, although it'll be less with each loop. So it'll be n-1 the first time, n-2 the second time. But really, it's probably easier to consider it as just being another operation in n. And flip front, this is doing 2 pieces of work, so moving an element forwards and moving an element backwards, and looping through half of not the array, but the input size n. So again, this will vary depending on where we're flipping in the array, but this input variable is what it depends on, and we do 2 bits of work for half the size of n. So again, this is an operation in n. And the same for this here. So 2 calls to the same function. If we take this all together, we are taking n, n, and n. So we're doing 3 operations in n. That's best thought of as a multiplier of n, 3n. And then at the top level, we're doing this many times, so n minus 1 times. So those 2 things we need to multiply together. And that gives us a complexity for time in n squared. The improved version doesn't do any better. So although we know we've saved some calls to flip front, the complexity hasn't actually changed. So we're still looping through the entire array, and we're doing an operation in n, sometimes an operation in n, and then definitely an operation in n. So although we reduce the number of calls, we improve the efficiency of the program. Depending on the input data, the worst case complexity for time is still the same. There are other sorting algorithms that are linear in n, or even logarithmic in n, which would be a better choice for solving this problem of sorting a list of numbers, but it's still an interesting problem to look at. Feel free to give a go to trying to improve the efficiency of the Pancake sort v2 and see what you can come up with to get the number of calls down.